Hello, let's take a look at some Chapter 4 problems. On this first one, we're looking at a gender selection technique where we have 250 baby girls, 275 baby boys, and we want to determine whether or not this selection technique increases the probability of a girl. First, you're going to take 250 plus 275. That's going to give you 525. Out of those, 250 are baby girls. So if you take 250 divided by 525 and simplify, you will get the probability that a girl will be born to this technique. Now, if that's relatively close to 50%, as it would be typically without any gender selection technique, then the method is not effective. If, however, it were significantly higher than 50%, then it would be effective. On the next problem, you have 8 possible outcomes listed for a couple that has 3 children, and they ask you, first of all, among 3 children, what's the chance that there's exactly one girl? 1, 2, 3. 3 of the options have 1 girl and 2 boys listed, so 3 out of 8. What's the chance that there are 2 girls? 1, 2, 3. So again, 3 out of 8 options. What's the chance that there are 0 girls or all boys? 1 out of 8 options. The complement of that, where you have at least 1 girl, are the other 7 out of 8 choices. Keep that in mind for a later problem. On this particular data set, we're looking at insurance results about accidents. We want to find the probability that a pedestrian was intoxicated or the driver was intoxicated. That means we are looking at this column, where people are intoxicated, and this row. Now, intuitively, you would recognize that you don't count those 80 people twice because they fell into both the intoxicated column and the intoxicated row. So if you want to do this without writing out a formal formula on paper, you will take 265 plus 80 plus 98 and divide it by 984. If you would prefer, you can use a more formal formula, and you can have the probability of intoxicated pedestrians, which would be 345 out of 984, plus the probability of intoxicated drivers, which would be 178 out of 984, minus the overlap, which would be 80 over 984. Either way, you'll get the same answer. On this one, we're looking at the complement, writing the complement for when 8 cell phones are tested, at least 1 is defective. That means 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 of them are defective. The complement of that would be that none of them are defective or all of them are free from defects and working fine. The next problem is similar. You have 13 digital pianos and one of them is defective. The complement of that would be that none of them are defective. If a couple plans to have 7 children, what's the probability that there would be at least 1 boy? Well, let's take a look at a couple having 2 children. There are 2 times 2, or 4 possible outcomes: boy, 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 girl, girl, boy, girl, girl. For a couple having 3 children, as you saw in a prior problem, there are 8 possible outcomes: 2 times 2 times 2, or 8. So for a couple having 7 children, there are 2 times 2 times 2 times 2 times 2 times 2 times 2, or 2 to the 7th total possible outcomes. Of all those possible outcomes, only 1 would be all girls. The rest of them would include at least 1 boy, so it's much easier to find the complement and subtract from 1. On this particular problem, we're asking the probability of a couple having a baby girl, given that the first 2 were girls. Keep in mind that births are independent. The fact that the first 2 were girls does not affect the chance of the third one being a girl. Each baby has a 50% chance of being a girl and a 50% chance of being a boy. However, the second part of the question asks us if that's the same as a result of getting 3 girls out of 3 children, and the answer to that is no. Think back to the problem before we looked at the 8 possible outcomes. Only 1 of those 8 outcomes was where you had a sequence of all girls. Now, this particular problem is one where we have a given condition. You need to be careful when you read this problem because it's 2 different things. If I ask you, for example, what's the probability that a person tests negative, and that's all I said, you would simply add all these up, get 300, and then say how many tested negative? 155 out of 300. I could ask you how many had the disease? 146 out of 300. Keep in mind, of course, you should definitely reduce those fractions. This problem, however, asks us the probability of getting someone who tests negative given that they had the disease. That means we are only looking at the 146 people who had the disease. Out of that, what's the probability they test negative? 10 out of 146. Oh yes, the lottery. We all want to win that lottery. Well, at least those of us who play. So let's assume that you're debating whether you should play the lottery or not. What are your chances of winning? Here you have 21 numbers and you're going to select 5 in any order. That means just a combination. You really don't need to use a permutation here because orders are irrelevant. So you use your calculator to determine 21, choose 5. Remember, it's a combination, not a permutation. Then only one of those possible outcomes would be the winning ticket. When testing for current in a cable with 6 color-coded wires, you could use a meter to test 2 wires at a time. How many tests could you have? Again, order doesn't count, so you're really looking at 6 choose 2 with a combination.